All right, the notes I have pulled up here are 2-1 day 2. And this is kind of a continuation now that you kind of know what a limit is and hopefully have had a little bit of practice finding limits graphically. Now we're going to start to get away from graphs a little bit, and what are some other ways we can use to find a limit? So we're going to look at some limit laws today. But just as an introduction, I want to kind of revisit what we did yesterday looking at graphs. There are two problems here, and quite honestly, for each problem, I used my graphing calculator. I graphed this one. This is kind of what it looked like when I zoomed in on it. But you need to know that your graphing calculator doesn't show you holes. So I didn't know that there was a hole there, but I kind of do because think about this. If I try to plug in 0, look what happens to me. So I know that something weird is going on at 0 in this particular function. So anyway, I graphed it. That's kind of what it looked like. And yeah, it turns out that from the left and from the right, both sides, this function, the y values are getting closer and closer and closer and closer and closer and closer to 1. Do they ever reach it? No, it blows up when they get there. But the limit is 1. Now, so for this function, as x approaches 0, my y's are headed toward 1. This is going to be kind of a common limit, and you need to have that memorized for your AP exam. Also for the homework that you're going to do, and possibly for the quiz and test. I really don't remember if that's on there, but memorize it. Also, think about this for a second. I'm going to say this. You're going to think this. I hope you think this is kind of cool. Do you know why this fraction, as x gets closer and closer to 0, so as these numbers get tiny, as these numbers get tiny, and we do our sine function on it, so as x gets closer and closer and closer to 0, do you know why this fraction gets closer and closer to 1? It's because the value of the numerator gets super close to the value of the denominator. Make sense? So like, what would 2.999999999 over 3.111111111, wouldn't that be really close to being able to reduce to 1? So that's what's happening. My numerator value and my denominator value are getting really close to each other. What happens if you turn those upside down? Does it matter? No. My denominator value and my numerator value are getting closer and closer and closer to each other, which means my fraction is being almost able to be reduced to 1. So it really doesn't matter, the orientation of this fraction. Now, 2 things before we move on. This limit answer is true when x is anything. How do I didn't say that right. This limit is true as long as what we're taking the sign of matches what's in the denominator. As long as they match, it's true. So I could be taking the sine of, x squared over x squared. the limit as x approaches 0 of this function is still 1. So as long as these match, your answer to your limit is 1. The next thing I want to point out is some calculus students get so proud of themselves because they've memorized this. Oh my gosh, they know this answer. They recognize it. They're like, oh, it's in my notes somewhere. I know the answer is 1. Well, some people get so overzealous that they forget that it's only, the answer is 1 only when you're doing a limit as x approaches 0. So this fraction has appeared in a quiz or a test somewhere, I don't know. And somebody, not somebody, people, several somebodies will see this and be like, oh, I know this. That's 1. I can cancel it and just call it 1. No, you can't. See this function? This is what the graph of it looks like. Is this graph 1 all the time? Absolutely not. Actually, it's never equal to 1. It blows up when x is 0, but it gets closer and closer and closer to 1 as x gets close to 0. So this is only true when this is out here. Just because you see this fraction doesn't mean anything. It's got to be using a limit. Okay, moving on. I gave you a really ugly looking limit to see if you could evaluate. So again, this is one of those cases where, darn, I wish it had a name, but it doesn't, so we have to just write the whole function right there. So the limit as t approaches 0 of this function. So I used my graphing calculator. I graphed it. That didn't help. I looked at an XY table, and so I thought, you know what? I'm going to, I'm pretty good with the table function on my graphing calculator. So I typed in x's that were super close to 0. So I typed in x's on the negative side, just underneath 0, closer. I got closer and closer and closer to 0, and I wanted to see what my y's would do. And then I jumped to the top of 0. So I went just above 0 and then came back down and came back down closer and closer and closer to it to see what my y's did. Well, you know your graphing calculator only gives you so many decimal places. So it was kind of hard to tell. So as x gets closer and closer and closer to 0, where do you think the y's are headed? Do you think that they're headed to 1.6667? Or maybe, because it's forced to round, because it's out of space, maybe it's headed to 0.16 repeating. Either way might be a good guess. Just wanted to show you that that was like an option on your graphing calculator, and I think we'll come back to this one a little bit later and I'll show you some really complicated way to solve it. Sounds like a blast. All right, now let's move down to limit laws. So here is where I get to show you what is legal when you're doing limits and what's not legal when you're doing limits. So I've got two boxes here. I've got the box on the left and the box on the right. They say the same exact thing. This one is mathy. This one is wordy. Mathy. Here we go. Ready? If you're in calculus, I hope you choose the mathy version. So it says, what if you're doing a limit and it looks like what you're taking the limit of appears to be like two separate functions added together. Okay? So it looks like I'm taking a limit of two things added together. It's legal to split them up into two separate limits. So I can do the limit of this function, find my answer. I can do the limit of this function, find my answer, and then add them together. That's limit law number 1. Limit law number 2, same exact thing, only with subtraction. If I'm doing a limit, it looks like two things are being subtracted. I can do each limit separately and subtract them. Limit law number 3. Suppose I'm doing a limit on a function, but this function has like a coefficient out in front of it, some constant. And I'd be like, man, I just wish the constant were out of my way so I could do this limit. You can pull the constant off. So I can pull the constant off, I can evaluate my limit, and then you can put the constant back on and multiply it in. So if the constant's in your way, pull it off, do your limit, put it back on, you'll get your answer. Number 4, kind of the same as number 1. If you've got two things being multiplied together, you can split them into two separate limits. And keep in mind, all of this is good as long as your limits do exist. If either one of these, we'll see later, if a limit doesn't exist, we'll see what happens. And then this one, if you're doing a limit and you've got two things that are being divided, yes, you can split them up. You can do the limit of the top and the limit of the bottom, as long as the answer to the bottom doesn't give you 0. Because y'all know, you cannot divide by 0. All right. So kind of common sense there on what we can and can't do with limits. So in this example down here, we are looking at two functions. F is pink, G is blue. You can see on mine, I darkened my axis because it's hard to tell. Like every line was the same thickness and it was just hard to tell where the origin was. So I darkened mine. Okay, pink and blue. And here's what it's telling us to do. So it's saying, let's do the limit as x approaches -2 of this one plus 5 times this one. So first of all, I used law number 1 to split these into two separate limits. And I used law number 3 to pull this constant off of g of x and put it out in front. Split them, pulled off my constant. And then, let's see, I evaluated. So I looked at the picture. As x approaches -2. As x approaches -2, where's the pink function headed? +1. Constant times. How about g of x? As x approaches -2, where is g of x headed? -1. Do the math. My answer is -4. Next one, I use law number 4. It's multiplication. I split them into 2. I evaluated the limits as x approaches 1. As x approaches 1, f was headed toward 2. And as x approaches 1, look at this. As x approaches 1 from the left, the blue is headed toward -2. From the right, the blue is headed toward -1. Do they match? No. So, as x approaches 1, this limit doesn't exist. So my answer is doesn't exist. And for the last one, I used law number 5. I did the limit on the top and the limit on the bottom. So, can I fit it on? There we go. F of x, as x approaches 2. Yeah, f of x. As x approaches 2, the pink looks like it's 1.4-ish. And as x approaches 2, the blue is headed towards 0. Both sides are headed towards 0. And that blows up, so the limit doesn't exist. Now, let's flip over to the back. There are more limit laws, and they look terrible. They really do. Looks like there's so many of them, and oh my gosh, you're going to have to memorize them. It's not going to be a problem. I guarantee it. It's not going to be a problem. So let me just go over some things that are legal. They're going to make perfect sense. When you're taking a limit of a function and your entire function is being raised to a power, you can kind of like forget the exponent. Just do your limit on your function, get your answer to the limit, and then take your limit answer to the power. So when your function's being raised to a power and it's getting in your way, you don't know how to do it, no big deal. Do your limit on the function, get that answer, raise that answer to that power. 7 and 8 are common sense laws. The limit of a constant. All right, so remember, this is where your function. This is where your function goes. Remember, what if your function is a constant? Like f of x equals 4. What if your function is a constant? Ready? As x approaches a, where's a? Doesn't matter. As x approaches a, where are my y's headed? 4. So the limit of a constant is just a constant. What if your function is actually x? It's not a quadratic, it's not a cubic, it's not some trig thing, it's just x. What does x as a function look like? You all know what it looks like. Ready? Suppose a is, I don't know, I don't care, somewhere. Suppose a is out here. As x gets close to a, where are my y's headed? Well, if this is a, then this is a, right? So the limit of x as x gets close to this number, if x is getting close to the number, y is getting close to the number. Number 9, this is really a combination of number 6 and number 8. With the whole power thing, number 6, and with the whole limit of x thing, number 8. Number 10. This is a combination of 6 and 8, but with 6, we're using like a fractional exponent. That's what gives us a root. And number 11 looks complicated, but it's not. It's just number 6 and number 10. So, limit of a function that's being rooted, just do your limit of the function. Get your answer, and then root it, whatever root you're taking. Not that bad. Okay, now, let's see. On this next example, it says we're going to find the limit of this function, and you're going to justify each step. That means for everything that you do in this problem, you need to tell me which law you're using. And yes, it does sound very yucky, but I promise you that we're going to do this once. If I go too fast, pause it and copy. Rewind if you need to hear me say something again. This is the only time we're going to do a limit while justifying each step. I promise. So, one time, we've got this. It's going to be yucky just once. Here we go. So I'm looking at this limit. It looks like I got stuff like added and subtracted. So I'm going to use one of my laws on the front to split them into pieces. So I split it into the limit of the first term minus the limit of the second term plus the limit of the third term. And then, let's see, what do I want to do next? I think I want to get this constant out to the front, and I want to get this constant out to the front. That was law number 3. Yep. Constant out to the front, constant out to the front. And then, see this power here? there was something about a power. I think it was law 6. Yeah, it was law 6. That said, is this in your way? Don't worry about it. Do your limit on just plain x. Once you get that answer to that limit, then you can square it. Okay, so everything stayed the same from here to here, except right here I used law number 6. Okay? Now, we are going to actually start evaluating. So this right here is a law that's up there. This right here is the same law that's up there. And this is a law that's up there. So this first one comes from law number 8. And the limit as x approaches 5 of x is just 5. Okay, so that stayed. That became a 5. That's still squared minus. The constant stayed. This is just 5. And then law number 7 said the limit of a constant is just the constant. Do the math. The answer is 39. I get 5 squared times 2 minus 3 times 5 plus 4. 39. As x approaches 5, the y values on this function are headed toward 39 from both sides. Okay, now I told you we're only going to do that once with all the labeling all the laws. You ready for this? Direct substitution property. If f is a polynomial, which in this case it is, or a rational function, and, this is kind of important, a is in the domain. Now wait, you know what that means? It means this number can be plugged in to my function without me blowing up. As long as I can plug in a into my function and get an answer, this direct substitution property works. And here's what it says. As long as all that happens, you got a polynomial or rational, as long as you're able to plug in this number, the answer to your limit is exactly what you get when you plug in the number. Where the y's are headed is exactly the y value when you plug in the number. Can I plug in 5 without blowing up? Absolutely. Plug in 5, see what you get. 25. 50 minus 15 is 35 plus 4, 39. No, we're not going to do all this. We're going to use direct substitution whenever possible. So, again, direct substitution. You want to find an answer to a limit? Take that number, plug it in, cross your fingers, hope you don't blow up. If you don't blow up and get an answer, that's the answer to your limit. Let's do one. Last one, evaluate the limit. Well, I'm going to suggest, limit here, I'm going to suggest try direct substitution and hope you don't blow up. So let's plug in this x value into my function. I didn't blow up. The answer to the limit is 2. Direct substitution. You're going to love it. Okay, that's it for day 2.